coming to like the past 3 or 4 like talks here in the group, and like everyone is like doing such an amazing job. So very honored to be invited here. So as you can see in the title, I'm gonna tell you about verification of Rust programs using liquid types. Most of this talk is like based on a paper that's currently under submission, so you can see the co-authors in like listed here. But I also threw in this like word ergonomic verification as a way to sort of try to differentiate the work from like other types of verifications, and as a way to motivate like the way I think about verification, because I think when I say verification, it's not what some people may think of. So what do I mean by that is that currently we're not like worried too much about like these like heavy like properties like functional correctness of programs, but rather something that we came to call like lightweight properties. So I'm thinking about like array bounds, like overflows, unreachable arms, like stuff like that. So in a way, I'm looking for like a minimal set of like features that you can add to a language that will allow you to like prove many of these properties that are like ubiquitous in like normal programming, and like without adding too much overhead to the programming, right? So, and within our solution, like the solution to this is like using types or refinement types for do the verification. So in the rest of the talk, I'm gonna first like give an introduction to refinement types and how they played out in Rust, like without worrying about mutation. Then like after explaining how Flux extends Rust with refinement types, I'm gonna explain like the the relationship that refinement types have with ownership, and then I'll like try to like as much time as I have like trying to show you examples. So what are refinement types? So this is what like ChatGPT has to say about refinement types. So a refinement type is a type system that adds constraints or refinements to an existing data type to ensure more precise and safer program behavior, which is, I guess, sort of true in some like broad sense. It gets right like the idea that we're trying to make types like more expressive by constraining the set of values a type can like refer to. And in practice, refinement types come in many flavors. So I'm gonna go over like all the flavors that we have in Flux. So the most basic or like the most fundamental refinement type in Rust is what we call an index type. We use this syntax. So an index type is formed from a base type and a refinement index. So a base type can be any of Rust types. Yeah, so we can have like an i32, a Boolean, a vector, and the refinement index is some expression in the logic, like a pure expression that can be of some sort, like the pure integers, like pure Booleans, maybe lists of like polymorphic sorts, stuff like that. As an example, we have like a i32 index by 10, which intuitively corresponds to the singleton set of i32 values that are equal to 10, or like the bool index by true, which is like the singleton set of Boolean values equal to true. I think like a initial intuition for this is think of index types are singleton sets, but we'll see later that you can use indices for like some other, they're not always singletons. So I want to stress that in Flux, there's a clear separation between like Rust expressions and logical or refinement expressions. And these index types are sort of like a way to bridge between Rust expressions and logical expressions. You can think of them like the index of a type to be like the model of values of that type. So you only express properties in terms of the model, like the index, and not like the values themselves. So a second, to give you some like intuition on how like type checking works with refinement types, we have like a set of syntactic rules, like this one, for example, which tells you that if you have two expressions and you want to add them, and you know that expression one is like i32 index by n and expression two i32 index by m, then you can give it a type I32 index n plus m. So this is mostly syntactic, but we throw in like what the like separates like normal type system from refinement types is like we throw in some like SMT queries, right? So for this rule to be valid, we need to like create the SMT solver to prove that the addition won't overflow. So what I'm trying to get here at is that like the typing rules are mostly syntactic in nature, as like in any type system, but we throw in some like queries to the SMT solver to add a bit more expressiveness. Another important one is like the rule for subtyping for index types. So the rule is very simple. It says that if you have a base type indexed by R1, that is a subtype of P indexed by R2, if you can prove in the logic that the indices are the same. So we can, for example, prove stuff like that 1 plus 2 less than 10, like that as a Rust expression has type bool true. Because like applying the syntactic rules, we can prove that 1 plus 2 less than or equal to 10 has type bool, 1 plus 2 less than or equal to 10 in the logic. And we can prove the subtyping that type is also a subtype of bool true. So another feature in Rust is that function types can be parametric on refinements. So we use this syntax, the add syntax, to declare a refinement parameter. And it's like bound in the entire scope of the function. So we can, for example, have a function like isPos that specifies that it takes an I32 equals to n and returns a Boolean which tells you whether that integer n is like positive or not, right? So here I'm trying to stress that the properties like the refinements are on these pure values and not on the values themselves. So we're not putting a constraint on the x value, like the Rust x variable, but on the index of the I32. You can think of it, so that was like the surface syntax. So internally, you can think of them as being like function type C parametrics on these, or like generic on these parameters. So what I'm showing here at the bottom is not like real syntax, but you can think of them as having like function types having this extra generic n, which is of sort int. So the next feature is what we call existential types. So existential types can be used to represent a set of values that satisfy some constraint. So if you've seen some other refinement type system, this may look more like those. Like if Liquid Haskell basically only has existential types, as I would like to say. But basically you are referring to the set of values, some set of values that is satisfies some predicate. So I think the easiest is to show you an example. So if you want to refer to the set of positive I32 values, you can use this existential type. So let's look a bit at how like the subtyping rules look for existentials, and I think it shows a bit why do we call them existentials. So if you have if you're proving subtyping between the two types, and you have like the existential on the left side, then you can, like for a fresh value x, you can assume like the property you have for that. So so this is like the rule we have. So this gamma is sort of like a logical, like an environment where we track all the like assumptions that we can make about values, right? If you have it on the right though, then you need to pick one particular value that you have, and then you have to prove the property for that value. And we set up subtyping in such a way that we can always pick the value by syntactically looking at the way subtyping is defined. So to finish with like existential type, we like post this sugar because like we restrict the value to be an index type, like the type there to be an index type. So it's like kind of like a bit redundant to always specify the index type. So we use this sugar syntax on the right. So here's another example. You can like write more concisely the like positive I32s like I am showing here. So the final refinement types flavor that we use is that what we call like a constraint type. So constraint type look a lot like what I showed you about existential types, but they don't have this extra refinement variable that you're putting constraints on. It's basically a way to attach a predicate or a constraint to a type. And I'm stressing here that that type can be any type as opposed to existential types that were only over index types. Yeah. So the rules for subtyping for constraint types are also very straightforward. If you have a constraint type on the left, then you can assume it and put it in your environment. You can assume that the predicate of property. And if this is on the right, then you have to prove it. Yep. So they allow us to sort of encode assumptions, and if you can think of them like precondition or postconditions in like normal like program logic, if you wish. So any questions so far? I think it would be a good time for questions if you have any. Otherwise, I'm gonna go and show you some of this stuff in how they played out. Okay, so I'm gonna show you some of the stuff I've been talking about. So let's suppose we have like this absolute value function. And we want to prove something very simple. So the way we specify refined types or functions in Flux is we're using these attributes, right? And we want to prove that something simple, that the result is like greater than or equal to 0, and that the result is also greater than n. So if we try to prove this, then we will get an error by Flux saying us that the operation may overflow, right? Because if we know that we can only negate some value if it is not like the minimum one, so we can put a constraint here saying that the value needs to be different than the minimum. So if you have that, then the function passes and it verifies. So at the use side, so if we try to call the absolute value with -1, then that's okay because like -1 is a subtype of the constraint type here. But if we try to call it with like I32 min, then we will get a precondition because the type of I32 min is not a subtype of the input type for the function absolute value. So next I'm going to show you like one of the major advantages of using refinement types over what we call like logic-based verification, right? So the thing with types is that they compose, so you can use them in any other place where you could use a type. So let me show you what I mean by that. So for that, I'm going to define a function that I'm going to assert. I'm just gonna, so this is gonna let us do like a static assertions. The function assert would just be a function expecting a boolean equal to true. Then to call this function, then we need to pass it something that we know statically it is true, right? And suppose we're gonna say something about positive numbers, I'm gonna define an alias for positive numbers. So here I'm defining an alias for positive numbers, and I'm gonna say I have a vector of positive numbers. And this is like a very dumb example, but it shows you a bit of the power of using refinement types. So just by the virtue of having a vectors of positive numbers and then iterating over those, I can prove this, right? And so if you're familiar with like how iterators are implemented, the code behind this is like very complicated. There's a lot of traits and a lot of going on in this the sharing of for, but there's nothing special going on in the refinement of those functions. Just by putting a positive number on vectors, then when I take them out of the vector, I can prove that they're positive. Yeah, I think we have some questions.
Yeah, I have a quick question. So, how can you do? Oh, okay, never mind. I think I answered my own question. It's because the refinement is on the type, so you know from the very fact that X is of type pos, you know that it's positive, right?
Yeah, exactly.
Okay. So you don't actually have you don't necessarily even know that X comes from that vector. Like the iterator could be producing something completely illegal or like using magic to get the values.
Yeah. Okay. So that has some advantages. You can like for free get this sort of a specification. Yeah. But also you're not actually tracking the values themselves. So there are some properties you basically only express quantified predicate over like that must be true over all the elements. But you cannot say, for example, like sortedness because you're not tracking the specific values. I think there's also a question in the chat. Is all the refinement types checking dispatch to an SMT solver behind the scenes, or do you run it without the custom parser first and only dispatch it once the simple reason? So we almost encoded directly to the SMT solver. One of the goals in Flux and with refinement types or liquid types in general is try to avoid having quantifiers. So we exploit, for example, polymorphism to get some of the benefits of having quantifiers, but none of the like the queries we throw at the SMT solver have quantifiers. I don't know if that answers the questions. I'm gonna show you a bit like the constraints we generate because it's like almost a direct encoding into SMT, except for like refinement inference. Okay, any more questions here? Because I'm gonna switch topics a bit after this.
I have a question.
Yep.
Why do we need to also assert call assert if the positive already has the like assertion in it?
I know. I just wanted to show you that I can prove this here, so that's why I.
Oh, I see. Okay. Okay, so it's not
example,
necessary. It's just an example.
Yeah, if I change this by greater than equal, then I should get an error because I cannot prove it. Yeah.
Okay.
Yeah. Okay. So that was like refinement type, like Rust and refinement types without mutation. So let's now see like the interesting part of this, right? Is like how refinement types play with ownership and with mutation. So one of my goals here is try not to be smart, right? So I'm trying to, let's just add refinement types to Rust and see what happens kind of thing. So I'm mostly interested in what do you get out of the box if you just throw in refinement types to Rust. Not try to be too smart with the ownership part. So like starting very basics, when you have exclusive ownership, you can do something called like strong updates. So let's consider this very simple example. So you have an integer that you initialize with 0, and then you mutate it to 42, and then you should be able to assert that the integer is equal to 42. As I was saying, because we have exclusive ownership, we can do something that is strong update. So you can actually change the type of some variable. So X starts being an i32 indexed by 0, and then we can update the type to i32 indexed by 42. So as you can see, I'm not actually tracking the value itself. I'm just changing the type associated with that value. In this case, because integers are very simple, it happens that like the type like exactly captures the value, right? But in more complicated cases, like the type will not be able to capture the exact semantics, so we'll have an approximation. The interesting one though is like what happens with mutable references. So I'm trying to ask answer the question like what's the meaning of having a mutable reference to an I32 index by 0 or a mutable reference to a I32 such that v greater than 0. And to do that, I'm gonna look at what I think is like the semantics of mutable references, like what they give us, and see how that plays out with refinements. So I think one fact is that subtyping of mutable references is invariant, right? So if you want like ampersand mu t subtype of ampersand mu t2, then you have to do the subtyping must hold both ways. Subtyping in Rust is like only concerned with lifetimes, right? But once we have refinements, like subtyping has it's a bit more interesting. So we're gonna keep this restriction that the subtyping of mutable references needs to be invariant. So what they give us out of the box is that with mutable reference, you can only do weak updates. So what do I mean by that? If I have a function, for example, decrement that takes a mutable reference to an S32 b greater than 0, then I cannot change the type of the thing point by R. So whenever I update it, I need to prove that what I'm putting in that location satisfies the type. So in a sense, a mutable reference allows us to attach an invariant to some data that needs to be true at certain points. So this may look like a restriction. I'm gonna try to convince you though that one, this is actually a feature like that mutable reference, you cannot actually change the type. And is also, I'm trying to argue that this is actually what mutable references gives you out of the box. That's the semantics of mutable references. But yeah, also I get that it is a constraint. I would like to write decrement in a way such that I know that the value, like after the return, after the function returns, actually it was decremented by 1. So we came up with this the concept that we call strong references that allow you to do that. It's basically doing a strong updates through a function call. So we have this notation for that. So for example, we can have a function increment. I think I made a typo, but the idea is that I take a strong reference to an S32n, and then I ensure that when the function returns, then the thing pointed to by R will be 1+, avoiding things about like overflow here. Internally, this is sugars to something like I'm showing at the bottom. Let me try to explain this bit by bit. So what I'm saying is that this function the sugars to something that is generic over some location and some integer. And then in the input, so we have an explicit heap. And I'm telling that at the input, the location points to an I32 index by n. I take the input of the function is a pointer to that L. So I precede information of like aliasing information. It's like a pointer to that particular location. And then at the output, I can update the type associated with L. So strong and mutable references have an interesting interaction. So we have this, I think there's a question.
Yeah, I guess I was a little bit surprised by mute. I guess intuitively, it seemed like you might always want strong. So I guess what are the advantages of mute? And like,
yeah, when you have mute in the return type, it's like completely different.
Mm-hmm.
So a mute and an unmute in input position is equivalent to with a strong that ensures like the same type at the output, right?
Right.
But once a mutable reference is in like weird locations, like for example, inside a vector or as the return type of a function, then it has a very different semantics. I'm going to show you when I show you an API for vectors that exploits that difference between mutable references and strong references.
Okay, thanks.
Okay, so we have this rule that allows you to go from a strong reference to a mutable reference. So I'm going to try to explain this rule. So if in your context you have a location pointed to some type tau1 and a reference which is a pointer to that location, then you can sort of weaken, like forget that you're actually pointing to that location by weakening the type T1 to some type T2, and then saying I'm only going to mutate R through this mutable reference that has type tau2, which is it's like a weakened version of tau1, right? So, and by virtue of the borrow checker, and because mutable reference only allow you to do wake updates, then we know that when we're done with the mutable reference R, the location L will have the type tau2. Yep. The thing is that, okay, I'm gonna try to explain a bit with this example, how that works in practice. So we have this very simple function. It has like two integers, x and y, initialize it to 0 and 1. And then we take a mutable reference to either one of those, like depending on some Boolean. And like assume like I do some mutations in between the assert, and eventually I want to prove that the value x is like greater than or equal to 0. So when I take in this mutable reference to x, what happens in Flux is that I initially take like a pointer to that. So I have this x, which initially has had type I3 to 0. And then R is a pointer to that X. But because I need to join both branches, I need to sort of weaken the context in a way that both match. So applying this rule that I showed you before, I can say, okay, I'm gonna weaken the type of X. It's not gonna be something 0, it's gonna be some I32 such that I'm using this pound K. It's like some predicate that I need to infer. Because I don't know when I'm type checking this branch, I don't know like what is the property that I'm not sure when I'm gonna do with the R, right? So I'm not sure like what type to give it. It is a weaker type. And I'm only gonna mutate R through this like weaker type. So we can like continue type checking with this weaker type, and we have a way in which we can like later infer those predicates. Yeah. So that's like the liquid part of Flux. Like using some like fixed point algorithm, we can infer these predicates that at this point we didn't know. Any questions so far? Yep.
Yeah. How can you infer the predicates, or how's that? I mean, is this like a partial procedure? Like you know, you can't infer every predicate, right?
Yes,
or you
actually.
Can't...
Actually, let me show you. I think I forgot to show you one of the examples, but let me show you how the constraint looks like, and and then when I show you the constraint, I'm gonna like tell you how we can actually infer that. So
okay.
Forgot to show you this example. Okay, I'm gonna erase this. So we have like GCD function. So what we're trying to prove is like absence of overflow here, and that we are like like the percentage operator never has a denominator of 0, right? So I'm gonna run Flux here in the console such that I can dump the constraint. And oops. Oh, what happened? Ah. No. Okay. That should do it. Okay, so this is the like the constraint we generate for the like the function GCD. Let me put it on your side. So you can think of it as a tree. If like a constraint have like the same indentation, they're like siblings, and also it's like a horn constraint. So these constraints have like some unknown variables, like these key variables, and there is this fixed point algorithm that will look for solutions to these key variables. Yep, and the way it does it is like by abstract interpretation. So it basically is going to look over solutions that are conjunctions of like predefined predicates. Yep, like and predefined predicates applied to the variables in scope. For example, for this particular example, what the thing we need to infer here is that A and B are always like positive. So that was something that it is predefined. We can infer that. And basically what it's inferring here is that the type of A and B in the head of the loop is that they are positive. Yeah, does that clarify it a bit? Yep.
Yeah, that explains it. I have some other questions about this, but I'll wait till the end.
Mm-hmm. There are nuances with that. So there's ways so we have a couple of, they're called qualifier, these predefined predicates. We have a couple of them like hard-coded. There's something we haven't done yet, but it has been done with liquid Haskell, is that by looking at the program, you can infer those qualifiers, because many times, like the properties you need to infer come from the functions you're calling, like the preconditions of functions you're calling. So you can sort of like scout them over the signatures of the functions you're calling. You can also define new ones, like you should use to define new ones. And also this fixed point thing comes into play when you have loops. If it is like a straight line code, you can do sort of like a strongest post condition, like rewrite of these key variables. And the actual algorithm is a mix of both. So you do a strong post condition rewrite for the cases you want, and then you end up with a couple of constraints that we call that are cyclic. And for those, you need to you infer them through an abstract interpretation. In any case, like going on. So now I'm going to show you a couple of examples. So I'm going to start by showing you an API for vectors. So we have this abstraction we call rvec for refined vector, which are vectors indexed by their length, right? So we are only gonna keep track of the length. Keep in mind though that these vectors are polymorphic, so they have that advantage I showed you before. So we can not just keep track of the length, but also keep track of some properties of the elements they hold, right? And I'm gonna do that like without using any quantifiers. So here I'm showing you like the functions new and len. So new is very simple. It just returns you a vec of size 0. Yep. And the length will it takes like a short reference to a vec of size n, and then will give back a u size of size n. So not too complicated. So Butch is a little bit more involved, right? So it takes a strong reference to a vector of size n and a value t, and then it ensures that the size will be 1 plus what it was at the beginning. And the one that I think is the most interesting is like the one that will give you like mutable access to some index in the vector. And here's where I'm saying that having a mutable reference in the output is like not the same as having a strong reference. So the type for accessing an index in the vector takes a mutable reference to a vector of size n, and an index it is valid. And then it returns a mutable reference to t. And the key here is that because we're returning a mutable reference to elements of type t, we know that users or like clients of this function needs to satisfy the invariants encoded in t. They can only do weak update through the mutable reference. So by virtue of that, then we can be sure that the vectors will continue to hold elements of type t, right? Any questions here about the API? Okay, so let's move on. I'm going to show you like a couple of examples of what I think are show that using this API is ergonomic. So there's a question in the chat. So the type won't be updated by the user if it is a mutable reference? Yes, so you can mutate the value, but you cannot change the type. Yes, although maybe you have time at the end. There's something with lifetimes here that I'm like avoiding, but maybe we can talk about that at the end. So with vectors, you can do stuff like that. So we have this function init zeros that initializes a vector. Oops, I need to import it. So we can prove, for example, that this function takes a u size equal to n, and then it returns a vector with only zeros and size n. And as you can see, we can prove this without any body invariance or anything. Like everything happens because we are inferring these like predicates, these unknown predicates. And a particularly like interesting example that we have is like the implementation of the KMP search algorithm. I'm going to show you here. So this one is interesting because in KMP you take a pattern, which I'm going to represent as a RVec of U8s of some size M, and then you construct a table with so this table has the property that has valid indices into this pattern, right? So we express that by this type that says that it's an RVec where all the elements are valid in the indices into that pattern. So they are less than M. And also the table itself is if of size M. So this is interesting because I'm quantifying over all the elements of the table, right? Without using quantifiers. It's just by virtue of polymorphism. There's another question. The init is a fun example. You would panic. Yeah, because like yeah. I mean that is being hidden in the actual implementation of VEC because anyhow, I'm trying to show you that so we can express like interesting properties with refinement types, like this one that is quantifying over all the elements of the vector. And in this particular case, we can do it without like any extra annotations. So the just doing refinement inference, we can prove this. I'm gonna try to contrast it with an implementation we have for KMP for Prusti. That it can show you that in Prusti we have to specify all these extra body invariants, right? And they're not trivial. This is a like quantified body invariant, right? But in Flux we just get it for free. We can like infer it. So the last thing I'm gonna show you, like before maybe we can take some, like open it for discussion, is that we also have a way to like build abstractions over these refinements, right? So we can refine, like user define the data types. So for example, we have this refinement version of an option that is refined by some Boolean that tells you if the like which is like the active variant, right? If it is either none or some. So the way to do that is that we have this way to refine each variance. You can think of it as a like GADD of some sort, which each variant can specify a different index for the return type, right? So in the none case, like the index is false, and in the some case, it is true. So we can prove stuff like if you have you can only call, you have a function that you can only call and grab if you know that it is some, and then we can prove statically that this arm is actually unreachable. It's a bit more of the same, but a bit more complicated. We have like a refinement version of a list, which is refined by its length. And we can see here that like in the const case, if you take a list of size n, then we will output a list of size n plus 1. So this is like the standard definition of like vectors in like Coq or like programming language like that, right? Like index types. And yeah, we can like verify all sorts of stuff. I think the kind of like the most interesting one for me is like append. We can do like an in-place append without any extra annotations. Yeah, and if we take a strong reference to the list, then we can ensure that the list will be have size n plus m at the end of the function. Yes, so there's a question. So the length of the list is essentially a statically known property that isn't known at runtime. Yes, exactly. So if you want to connect them, then you have to do it explicitly, like here, where I'm saying that if I call len, then I will actually get a len, which is the same. We're looking at ways in which we can like derive this refined version up top by defining the length function. Otherwise, you get like these duplications in which you have to define the index and then give them like a runtime meaning by like basically replicating the same definition. So we're looking into ways that we can avoid that. Yeah, but I think that's everything I have prepared. Maybe we can leave some time for discussion now.
Thank you very much, Nico. This was very interesting. So yes, if anybody has any questions, I'd like to invite you to go ahead and ask them now. We have some extra minutes. So Dominic has a question. Go ahead.
Hi, thanks for the talk. Very interesting. I have a question concerning functions that take mutable references, like where you can change the type. So how would you ensure that if you like reborrow one field of the reference type, and you change that, then how would you like see that these like mutation doesn't change the type of the mutable reference?
So are you worried about the function reborrowing and returning a mutable reference to the thing that you took as an input, or reborrowing?
Modifying part of like a struct, for example.
Yes, so that's like the lifetime thing. So I show you that we can go from strong to mutable, right? And we were able to get away with that without reasoning at all about lifetimes, which I think is kind of nice. But in many cases, you do want to break the, when you have a mutable reference, you do want to break the invariant temporarily, right? And then reestablish it. So we haven't implemented that now, but I mean, in theory, I know how it should look like. I just haven't had time to implement it because like extracting the lifetime information from the compiler is impossible. But the thing is that when you have a mutable reference, you can temporarily see it as a strong during, as long as you like close it back before the lifetime ends, right?
Yeah, makes sense. But
yes, I haven't implemented that. It's like in the very high on top of my to-do lists.
So right now like how do you check that the invariant is like not broken?
Basically right now you have to either there are many situations in which you don't need to change the refinement at all, like the type at all. For example, we're looking at like ways in basically have like an implementation using refinement types of like ghost cell, and in that situations you only want like the brand, so you don't need to change it. So in those situations you can get away by not changing the type, and refinement types will still help you. Yeah, for more complicated cases, for example, where you have a mutable reference to I don't know, like an empty vector, and you want to push something to it and still be a non-empty vector, we don't support that right now.
Okay, thank you.
There's a question in the chat. Does doing things in Rust change simplify the inference as compared to liquid types or other languages? And if so, how? Yes, so I think one very major difference between liquid Haskell is that mir is typed and it has like all the like trait information, as opposed to core in Haskell that like basically throws away all the traits. I think that puts us in some advantage because we've been looking at it, but it's like easier to refine the traits. It took a long time to be able to do that in liquid Haskell because core doesn't have like the trait information. Also, closures are hard in Rust compared to Haskell.
So there's also another question from Jared, who was asking if we could see some examples of it failing to compile because it breaks one of the invariants.
Yes, so I'm going to show you a simple one. So the like Decker example will be like one, for example. No, so if I have a mutable reference to a positive number and I just try to subtract from it, well, in this case it fails because it could have overflow. Not because the invariant is failing. So maybe let me disable overflow. Settings.
I'm not sure I understand why it would overflow. Because if it's positive, you should always be allowed to decrement, right? Because at worst it could be 1 and you can always go to 0.
Yeah, there may be a bug. So we only currently, so I tweak some stuff in the code for just the talk. So there may be something going on there.
The demo effect, it happens to us all. There's a question from James otherwise.
Yeah, I guess I was curious if you have support refinement, reflection, and like lifting Rust to the logic in any way. I mean, I saw you reference like is_sum and lang in the refinements for structs, but yeah, what's the support for that?
No, I mean, we're looking into like using like zero-size types to kind of carry proofs for some stuff. So we've been looking at, like, for example, at the ghost cell, like example, we have like an implementation of that with using refinements. We also have something that we call like frac blocks that is, if you're familiar with static RC, it's sort of like an implementation of that using refinement types. And those use like ghost parameters to keep track of these proofs, right? As of like full reflection is definitely something that we want to do. It's way more complicated to do it in Rust than in Haskell, right? But I imagine that it will end up looking a lot like Verus in that stuff. I mean, those guys are basically trying to figure out what is the fragment of Rust where you can do proofs in, right? So I think we'll end up looking like that, maybe.
That's funny because I was actually about to ask you a question like about exactly that. Sorry, James. I don't know if you had any follow-ups.
Nope, that was it. Thanks.
Can you have indices that appear on the right-hand side? Like can you return indices that don't appear in your arguments? Can you sort of be generative with indices?
Yes. I mean, I'm gonna talk about the feature. So we have a feature where you can have sort of existential indices in the return type. So we have this syntax. So we haven't used it for too many stuff, so I cannot think of like an example of that. But
just return a pair of integers where you know that they're both some value n.
Yeah, so we have this syntax where you can. This is like a not very useful type, but you can return an integer, which is this like pawn. It's like an existential one, so it's like quantified just in the output. And yes, that should allow you to like return a pair, like dependent pairs, for example. It will allow you to encode dependent pairs. In the core implementation, like we actually have like a generic existential type where there's a, so we have this type which there's exists some n such that an arbitrary type. But the surface syntax doesn't have like good ways to expose that yet. We are looking into ways in which you can have existentials in more situations.
Okay. Very cool. Are there any further questions? All right. If not, I think we can wrap that up. Thank you again, Nico.
Actually,
sorry.
I just had a question. How like production ready is this? Is Flux?
So we have a like the more complicated thing we have verified is this system called Wave that like a guy in our lab verified. It's a verified like sandbox library for WebAssembly, and he verified it in Prusti. And the type of properties they're enforcing is that it's like basically array bound checking. They're proving that you never get out of the like the sandbox memory. And they also prove some stuff about like symbolic links being fully resolved to something that is within the sandbox. So they verified in Prusti and reported to Flux. So I don't know if that answers the questions, but that's like the most complicated use case we have for it right now.
Yeah, yeah, yeah.
I mean, one of the things we're looking at now is stuff to verify. If you have any ideas, we welcome to try them out.